Welcome to The Explainer. Today, we're embarking on a genuinely fascinating journey to decode the invisible forces that dictate exactly how the physical world around us behaves. I mean, if you've ever wondered why ice melts, how water turns into steam, or why you can instantly smell perfume from all the way across a room, you are absolutely in the right place. We're going to break down the fundamental rules of matter, taking a highly structured visual tour through some truly incredible concepts. So let's start right at the source. We're looking at the first chapter cover of the 10th class chemistry textbook from the Punjab Education Curriculum Training and Assessment Authority, or PECTA for short. It's basically the gateway to understanding how our universe behaves. But I want to try something here, a sort of cover to concept experiment. If you were to crack open this book and distill its core message about matter down to just one single fundamental rule, what do you think that would be? Well, the secret hidden inside these pages is the fact that absolutely everything, every solid, every liquid, every gas is constantly moving. Even the device you're using to view this explainer is made of particles vibrating at this very second. This is known as the kinetic particle theory, and it's literally the key to unlocking everything we're about to discuss. Okay, let's lay out our roadmap for Chapter 14, States of Matter and Phase Changes. We'll cover 1. Defining the invisible, 2. Changing states of matter, 3. Graphing the heat, 4. Evaporation versus boiling, and 5. Diffusion in our world. Starting with Section 1, Defining the Invisible. Because to understand the world we can see, we have to scale down to the microscopic particles that actually make it up. The textbook defines a crucial concept right out of the gate here: internal energy. Now, internal energy isn't just one single thing. It's the total energy a substance contains, and it's basically a sum of two distinct parts. First, you have the kinetic energy. That's the energy of the moving, vibrating, or rotating particles themselves. And second, you have the potential energy, which comes from the attractive bonds holding those particles together. According to the kinetic particle theory, when you add heat to a system, you are directly increasing its internal energy. You're pumping energy straight into those tiny particles. And if you pump enough energy in, those restricted, tightly bonded particles in a rigid solid will break their bonds and eventually become freely moving gases. Moving to Section 2, Changing States of Matter. We know heat increases internal energy, but let's see how that energy practically forces matter to transform right before our eyes. Let's walk through how this builds step by step. I want you to imagine a solid as a seated theater audience. Everyone is in a fixed chair, right? They can wiggle and vibrate in their seats, sure, but they are locked in place by strong, cohesive forces. That's a solid. Step 1 is melting. When you apply heat, you increase their kinetic energy. The audience starts vibrating at a higher frequency until, eventually, that movement totally overcomes the cohesive forces holding them in the chairs. The solid collapses and turns into a liquid, an audience now mingling and walking around the lobby. Step 2 is boiling. If you keep heating that liquid, the energy increases so much that the particles overcome almost all attractive forces. When the liquid's vapor pressure finally equals the external atmospheric pressure, it boils. Our audience basically bursts out of the theater doors, running freely in all directions. That is a gas. And step 3, condensation, is simply the reverse. If you cool the gas down, you're taking away that kinetic energy. The particles slow down, the attractions take over again, and they're forced right back into that liquid state. Section 3, Graphing the Heat. Now that we've got the physical steps down, let's see how scientists actually track this mathematically. But actually, before we look at the data, I want to pose a real-world question to kind of spark your curiosity. Picture this. You have a pot of water on the stove. You turn the burner on high, the water heats up, hits 100 degrees Celsius, and starts boiling vigorously. But no matter how long you leave that stove on, or how high you crank that dial, the liquid water itself simply will not get hotter than 100 degrees. Why is that? I mean, where is all that extra heat from the stove actually going if it's not raising the temperature? Well, the answer lies in the heating and cooling curve. When you map this out, you'll notice these perfectly horizontal, flat plateaus on the graph. When you heat a solid, the temperature rises until it hits its melting point. But right then, something amazing happens. You are still adding heat, but the temperature line is completely flat. The brilliant insight here is that during a phase change, like melting or boiling, the added heat is entirely used up, breaking the attractive bonds between the particles, not raising their temperature. So back to our stove. When water hits 100 degrees, every single ounce of heat energy from your burner is being used to tear the liquid molecules apart to form a gas. It's only after the entire pot has turned into steam that the temperature can finally start to rise again. Isn't that wild? Section 4. Evaporation versus boiling. Understanding how boiling works leads us right into clearing up a super common misconception. People often confuse evaporation and boiling, but they are entirely different beasts. Let's talk about location first. Evaporation is a subtle, surface-level phenomenon. Particles only escape from the very top of the liquid. Boiling, however, is a violent phase change happening throughout the entire liquid, which is exactly why you see bubbles forming at the bottom of the pot and rising all the way up. Next is temperature. Evaporation happens all the time, at literally any temperature below boiling. A puddle on the sidewalk dries up on a cool day without ever reaching 100 degrees, right? But boiling only happens at one specific temperature, the boiling point. And perhaps the most interesting part, evaporation produces a cooling effect. That's because it uses the internal energy of the liquid itself to allow the surface particles to escape, which leaves the remaining liquid slightly cooler. This is exactly why sweating cools you down. Boiling, on the other hand, requires a massive, constant source of external energy, like a stove, and it absolutely does not cool the liquid down. And finally, Section 5, diffusion in our world. We've talked about turning a solid into a gas, but what happens when those incredibly energized, fast-moving gas particles are let loose? That brings us to diffusion. We know the melting of a solid ice cube is driven entirely by temperature overcoming cohesive bonds. But diffusion is different. It's the rapid, spontaneous, natural spreading out of particles. But here is the fascinating twist that the kinetic particle theory provides. While temperature drives phase changes, it's the actual mass of the particles that dictates how fast they diffuse. The textbook points out that at the exact same temperature, all gas molecules have the same average kinetic energy. But because a gas like hydrogen is physically much lighter than a gas like oxygen, the hydrogen molecules literally have to travel much, much faster to maintain that same energy. Therefore, lighter gases diffuse significantly faster than heavier ones. It's a fundamental rule of how these particles behave in space. So, what does this all mean for us? Well, this isn't just theory confined to a chemistry textbook. If the mass of a particle dictates exactly how fast it diffuses through a space, imagine how absolutely crucial this kinetic theory is to the medical field. The textbook actually asks us to consider the diffusion of medicines in the body. When a life-saving drug is administered, its molecular mass and the internal energy of your body literally dictate how fast that medicine can spread through your bloodstream to the very cells that need it. These fundamental rules, internal energy, phase changes, breaking bonds, and diffusion, they govern